Okay, good morning. Week 12, we got another, including this week, another 7 or 8 lectures to go. So today's agenda is I'm going to complete the example on design of beams under combined loading. We have done the shear force and bending moment diagram. We also have formed the shear force and bending moment equations. Then next, I realized that when we were doing shaft design, I forget to show evidence why we ignore the shear force. How significant is the shear force? I'm going to do that. And we're going to start a new topic that is related to 3D mold circle. It's known as the yield criteria for ductile materials. Okay, so mold circle, like today's example, we also have mold circle. It's all incorporated, intertwined. Okay. So the example that we did on Friday is that we have an overhanging beam, and we managed to find the shear force and bending moment equation, and we also have sketched the shear force and bending moment diagrams. Okay. So now the thing is, when we are going to calculate the principal stresses acting on this material or acting on this beam, okay, which point do we need to calculate, right, relative to the shear force and bending moment diagram? Okay. Before I carry on, I'd like to emphasize, if we look at the cross-sectional area, if we were to look at the cross-sectional area, we know that failure will occur at the intersection of the web and the flange. Okay, that's where failure will occur. So we want to use two equations. We have to employ two equations. Okay. So the first equation is normal stress in the x direction is equal to my over Iyy multiplied by z. Okay. And then we are going to find the shear, okay, is equal to By over Izz Qz by T. Okay. The question now is this. What is My and what is Vy? Okay. And as you can see on our shear force and bending moment diagram, okay, as you can see over here, let's pick the maximum normal stress, right? We know that the maximum normal stress is over here, which I'm circling now in red. But it happened to have 0 shearing force. Yes or no? Right? Remember, I highlight the fact that the maximum shear stress will not be at the same position as the maximum shear force. Right? Okay. So the material can either fail in normal stress or shearing stress, or a combination of both. Okay. Then that is one point we're going to check. The other point that we like to check is where the shear force is maximum. Right? Where the shear force is maximum, the bending moment is not that high. But we still have to check. As engineers, we have to check. Okay, we have to validate, we have to check. And then the next point that I will like to consider, right, is this point over here. Okay, I pick a third point because it has a good mix of shear force and bending moment. Okay, so the bending moment is not low, but you also has a high value of what? Shear force. Okay, so those are the position we're going to check. So the position we're going to check is when x, okay, we're going to check when x is equal to 0.8. We're going to check x is equal to 2.4. And we're going to check x is equal to 3.2. So if we look at our stress x, so we're going to check at point, okay, we're going to check when x is equal to 0.8 meters. So the calculation is very repetitive. Okay, we're going to check when x is equal to 0.8. When x is equal to 0.8, Vy is equal to what? 80. I think it was 80 times 10 to the power 3 Newton. And our mz is equal to 16 times 10 to the power 3 Newton meter. Okay. So stress x at 0.8 is equal to my over Iyy multiplied by z. We know that, sorry, mz. What am I doing? It's all wrong down here. It's mz over izz multiplied by y. I will do the one on top, mz over izz multiplied by y. Okay. So mz is 16 times 10 to the power 3. Izz, so izz is equivalent to our ixx over there is equal to 40.1. Y, okay, so we have to calculate y, okay? So y is d, so d is 0.25 divided by 2, right? 0.25 divided by 2. And then we have to minus the thickness of the flange, right? Which is 10 times 10 to the power minus 3, right? Because we at this location, this is the point of interest, okay? Exactly down here is our y, okay? So it is the entire depth divided by 2 minus 10 times about. So I'm going to, so we know the y and izz value is going to be the same. So I'm, for simplicity's sake, for calculation later on, I will calculate 10.25. Is it D.25 or 259? 0.259. My apologies. Minus by 0.259 minus by 10. Okay. So 0.259 divided by 2 minus 10 power minus 3 divided by 40.1 power minus 6 is equal to 2.98 times 10 to the power 3. I will do that again, okay? 0.259 divided by 2 minus 10 power minus 3 divided by 40.1 power minus 6. 2.98 times that. So the stress, 16 power 3 times 2.98 power 3 is equal to 47.68 times 10 to the power 6 Pascal. I do it again, 16 power 3 times 2.98 power 3. 47.68. Yep, 14.68. Okay. Then we are going to calculate our shear at 0.8. So our Vy is equal to 80 times 10 to the power 3 divide by 40.1 times 10 to the power minus 6. The thickness is the web, and the thickness of the web is 6.31 times 10 to the power minus 3. This is from the table. Okay. Now is our first moment of area. So is BF, which is 0.102 multiplied by the depth of the flange, which is also equal to 10. Then multiply by 0.259 divided minus by 10 times 10 to the power minus 3 divided by 2. Okay, so this is your width, depth, and this is your y bar. Okay. So I'm going to calculate what will change in the later equation is the value of the shear force. Okay, the rest will remain the same. So I'll calculate that value. So later on, our calculation will be faster. Minus 10 power minus 3 divided by, by 259 divided by 2 minus 10 power minus 3 divided by 2 times by 0.102 times by 10 power minus 3 divided by 40.1 power minus 6 divided by 6.35 power minus 3 is equal to 498.714. Okay, I'll do it again. 259 divided by 2 minus 10 power minus 3 divided by 2 times by 10 power minus 3 divided by 0.102 divided by 40.1 power minus 6 divided by 6.35 power minus 3. 498.714. So this will be equal to 80 power 3 times by 498.714 is equal to 39.897 times 10 to the power 6 Pascal. I'll do it again. 80 power 3 times by 498.714. Okay. So I'm going to highlight this value because this value is going to be repeating based on any points that I choose. Okay. And these are the values that we have. Okay. So if we were to draw an element or the element, okay, we know that we have, it can go either way, okay? The tension on compression will be fine because the geometry is axis symmetry. Okay, so we are more concerned with the magnitude rather than what direction is in. Okay, so this is equal to 47.68. Right, and then we have 39.897. So because of the orientation of our diagram, wait, I'm thinking about this now. Maybe I'm drawing in the shear force is coming down in this way. Okay, maybe I'm drawing the wrong orientation. My bad. Okay, you know what? For simplicity's sake, let's draw this in 2D. Okay, so this is going up by 47.68 times 10 to the power 6 Pascal. And this will be going at 39.897 times 10 to the power 6 Pascal. Okay. So if we were to use if we were to construct our 2D mold circle, right, this is just a sketch. Well, let me sketch properly. So I need to make sure it's a circle. Okay. And we can check later on, is our in plane, right? The maximum. Okay, we have to, we can check easily. So this is our normal stress. Julia, for MZ, why didn't we make it 16? And for the tau, why do you use 80 instead of minus 40? 80. Julia asked the question, and minus 40. Julia, I'm checking at point X equal to 0.8. Okay. So I'm using the 80, the bigger value, and I'm using the minus 16. I'm using the minus 16. Yeah, I'm using the 16. Julia, does that make sense? You don't use the smaller value. You use the bigger value at X equal to 0.8, Julia.